Hello dear students, I hope you all are healthy, happy and working really hard to get your dream seat in your dream medical college. See here today we are doing the thermal expansion, but for solid we have already done, it's for liquid and gases. And to start with, we will start with the concept of volume expansion. What is volume expansion? Volume expansion is the expansion in either length or breadth or height or two of them or all three of them. See, it is not necessary that when we talk about volume expansion, all three dimensions must expand. If only one is changing, then also volume will change. So, okay, we will start with the concept of coefficient of cubical expansion, and that is being denoted by gamma. What is gamma? Gamma is 1 by V naught, initial volume, dV by dt, T is temperature. Or we can say dV by V naught, that is the change in volume upon the original volume, volumetric strain. So volumetric strain per unit change in temperature, this is also coefficient of cubical expansion. By changing the temperature by 1 degree Celsius or by 1 Kelvin, what is the change in volumetric strain? Okay. V from this is V naught 1 plus gamma delta T, and V naught is the initial temperature, V is the final temperature, just like the aerial or linear expansion. Now, as I was saying, to have your volume expansion in a 3D object, it's not necessary to change all the three dimensions. To explain this mathematically, I mean, what is the relation between gamma to alpha, whether gamma is equal to alpha or gamma is equal to 2 alpha or gamma is equal to 3 alpha, we will do a derivation. That derivation is, see, this is the cuboidal body and its volume is L1, L2, L3. Okay, at any instant, if we are calculating dV by dt, rate of change of volume with respect to temperature, it means what we are doing, we are actually differentiating L1, L2, L3 at any certain instant, certain temperature. Three product, okay, product rule, leave L1, leave L2, differentiate L3 only. Plus leave L1, leave L3, differentiate L2 only. Then leave L2, leave L3 and differentiate L1 only. See, one thing is very interesting to see here. These are the actual addition of three different expansions. So volume expansion here is sum of three different expansions. And moreover, suppose any two of them, like first or second or third, any two of them is 0. Even then also dV by dt is not 0. So have dV by dt, you might have all three, you might have any two, or you might have any one also. Okay, so this is dL3 by dt. By the concept of linear expansion, this can be written as L1, L2. dL3 by dt is alpha L3. Similarly here L1 L3, dL2 by dt is alpha L2, and L2 L3, dL1 by dt is alpha L1. So this is 3 alpha L1 L2 L3 and L1 into L2 into L3. What was that? That was this volume V naught. So can we write dV by dt here? See, 1 by V naught, you can write it as 3 alpha V naught, and 1 by V naught dV by dt, that becomes 3 alpha. So it explains gamma is equal to 3 alpha. But having said that, again, we have to understand, suppose if this length L1, this has been fixed, and it is not allowed to expand, then what will happen? Only L2 and L3 will expand. So in that case, gamma will equal to 2 alpha, or gamma can be equal to alpha also. So the concept, this gamma equal to 3 alpha, this is only applicable when all three lengths are changing. Otherwise, we can write gamma is equal to as many alpha as many lengths are changing, as many alpha, as many lengths are changing. So you have to actually see how many lengths are changing in that. As many alpha, as many lengths are changing. So in gamma equal to 3 alpha question, make sure see with concentration how many lengths are actually changing there. Now let's see some application points on volume expansion and how the expansion in solids and liquids they actually take place. Okay. See application point number 1. These all are the question points, important question points for your NEET examination. The first one is, while writing gamma, you must have noticed this is 1 by V dV by dt. Okay. So basically, when you will see this formula of gamma, it's quite evident that volume is changing with respect to temperature. And if volume is changing with respect to temperature, there is a thermodynamic process involved, which is changing the volume. Temperature change, then volume change. Okay. So that you have to understand by what process volume is changing with respect to temperature, and then accordingly gamma will vary. For this, we will see some examples. Suppose example 1. What is gamma? Here gamma is coefficient of volume expansion. It is not adiabatic coefficient here. What is gamma for an ideal gas? What is gamma for an ideal gas? This is the question. For an ideal gas. Now we have to think, okay, for ideal gas how volume is changing with respect to temperature, and there PV is equal to nRT. So obviously what will be the volume there? Volume will be nRT by P. This is the volume. And from volume, you know volume, from here you can find dV by dt. So what is dV by dt? dV by dt is equal to its rate of change, and that is nR by P. So we have V, we have dV by dt. What is gamma? Gamma is dV by dt divided by V. That is nR by P divided by V means nRT divided by P. And from here you can see that for an ideal gas, gamma for an ideal gas is equal to 1 by T. Okay. Here see equation is this. In NEET they might also ask you the graphical aspect. So from there you can draw the graph. This is gamma, this is temperature, and the graph is rectangular hyperbola. Okay, for ideal gas. Suppose they are changing the thermodynamic process. The thermodynamic process is now, suppose for second, if pressure is proportional to T raised to power minus 3, then find gamma. Now gamma is required when pressure is proportional to T raised to power minus 3. Obviously the process would be polytropic, but what is gamma from here? For gamma, do remember you have to see volume, and if volume is not there, you have to introduce volume there. How to introduce? See what is given. Given is P T raised to power 3 is equal to constant. Just name this constant something. Say this is K. PT3 is constant. What we need? Volume and temperature. So what is to be eliminated here? Pressure. So pressure from ideal gas we can write nRT by V. This is P into T cube, that is T4, and this is constant. Basically volume is nRT4 divided by K. So now we have volume and also volume with respect to temperature. Whatever is given, if gamma is required, what you have to do is to find volume as a function of temperature. And when you will do this, dV by dt, what you will find? This is 4 nRT3 divided by K. Now you have volume and you have dV by dt. What you have to find is gamma, that is 1 by V into dV by dt. And from here what you will do? You will put V here and this value here. What you will get? You will get 4 by T. Again the graph is like that only, rectangular hyperbola. So obviously slope will be a little different. So basically whenever a thermodynamic process is given, or some quantities like PT relation or a PV relation, what you have to do, you have to find VT relation and then you can find gamma. This was the first application. In second application, first application was this, to find gamma for according to a certain thermodynamic process. Okay. Now for second application, what we will try to see here, we will try to see effect of temperature on density. This is the second application. Okay, effect of temperature on density. In this you can see mass is equal to density into volume is constant. Okay, so partially differentiating this, we can write rho dV plus V d rho is equal to 0, which gives us d rho by rho is minus dV by V. This expression is also important for question point of view, how the fractional change in density is related to fractional change in volume. Now, what this minus sign is indicating here, volume is changing with temperature, so at the same time temperature changes density also. But minus sign is indicating that the trend of change of volume and density are different altogether. So if volume is increasing with temperature, density will decrease there. So in this way we can write final density is initial density 1 plus gamma delta T. So basically density decreases with increase in temperature. Here one more thing, at times you will see this equation written as like this, rho I 1 minus gamma delta T. You might see this equation written like this also. Let me tell you, these two equations are not always the same. Actually, when this gamma is defined for solids, what will happen? Solid volume expansion is very little, negligible. Obviously the expansion of liquid and gases are more than the solid. So volume expansion is taking place in liquid, gas and solid, all three. But expansion coefficient is obviously greater for liquid and gases. So in solid expansion is very little. Expansion is little, it means their gamma is very less. And when gamma is very less, then you can 1 plus binomially, 1 plus x, 1 plus variable, and that variable is very less. Then power becomes coefficient. So let me tell you one thing. This formula 1 minus gamma delta T, this is only applicable for solids. If in question liquids are given, gases are given, you have to write rho final is equal to rho initial 1 plus gamma delta T. You cannot write this. So this is for solids. So gamma S is volume expansion coefficient for solids. This is for solids. Solids you can use this. This you will have to use for liquid and gases. Let's see a question numerical on the basis of density formula with respect to temperature that we have just discussed. You can see a liquid column in the question and there are 4 limbs, different lengths for first and last, second and third are having the same length. Also temperature variation you can see for each individual limb, and question is asking you find coefficient of volume expansion of the liquid. This is the question. Now see how to solve this. You can see that both the cross sections are open. This is open and this is open also. Both are open. If both the cross sections are open, it means the pressure over there is the atmospheric pressure, right? So here the pressure is atmospheric pressure, here the pressure is atmospheric as well. Name it like A and this as point B. Suppose you are moving from A towards B, like you are going like this, then this, then this, then this. So you have started from where? Atmospheric pressure, and you are reaching finally where? atmospheric pressure. So basically pressure at A is equal to pressure at B. So whatever changes are there, like in first limb you are going on depth, in second limb you are going at height. So depth is basically increasing the pressure, height is decreasing it. But since the final pressures are same, it means, can we say that the changes made by the depth and changes made by the heights, those changes, those gauge pressures are same. So we can write pressure due to depth, gauge pressure due to depth, and gauge pressure due to height. These two must be same. So in first case we can write due to depth, what I will write, rho, and don't forget this rho is at 95 degrees Celsius. G, and in place of H it will be L1, rho GH. Also the depth in the third limb, that is rho, again that rho is at 95 degrees Celsius. G, and the length is L. So this is the total pressure at the depth, due to depth. Now due to height, second is due to height and fourth is due to height. So what we will write in place of height is rho 5 GL plus rho 5 GL2. So we can write finally rho 95, G will be cancelled, L1 plus L is equal to rho 5 G is cancelled, rho 5 L2 plus L. The G will be cancelled, so need not to write this. Now see, rho 95 is at higher temperature obviously, and temperature difference is of 90 degrees Celsius. So can we write rho 95 as rho 5 initial 1 plus gamma into 90 into L1 plus L is equal to rho 5 into L2 plus L, and from here rho 5 will be cancelled, and this expression easily gamma can be find out. One thing you will see here, first if both limbs are open, then there is a new trick, you can use pressure at depth equal to pressure at height. Okay. Second thing, here what formula we have used? Rho initial 1 plus gamma delta T. We did not use rho into 1 minus gamma delta T because first of all it was not solid, and second the volume coefficient, the coefficient of cubical expansion was not known to us. So we cannot use, okay, this is very small. When this is not known, how can you assume that this is very small? So here this formula will be used. You cannot find by that rho in 1 minus gamma delta T. So this was the question based upon the density expansion. Now one more thing we will see, how the aquatic life is safe. And for that you have to remember that in density expansion it will continue. Like this is temperature, this is density. What happens with water? Shows anomalous behavior. What anomalous behavior? This is density of water, and from 0 degrees Celsius it is increases till 4 degrees Celsius. There the density of water becomes maximum, and after that it's same, like density is decreasing with increasing temperature. So water's temperature, water's density, not from static, it is decreasing with respect to temperature. It first increases up to 4 degrees Celsius. This is why doesn't matter what is the outside temperature. Suppose we are talking of some water body like ocean and all. So it doesn't matter what is the temperature outside. The depth temperature will be always 4 degrees Celsius because density there is maximum. This is how aquatic life is safe. Suppose some ice layer is there, frozen, then what will happen to the aquatic life, the animal, water creatures? They will go in the depth. There water is maintained at 4 degrees Celsius and having maximum density. Moving to the next application point is effect of temperature on the buoyant force. See, first we will write the derivation of the definition, the expression for the buoyant force, that is density of liquid, volume of solid immersed into G. Why I am writing volume of solid? Because see, it's volume of liquid, but that volume is not defined for materials, volume is defined for space. So whatever volume of liquid is being displaced is equal to the volume of solid that is actually being immersed. So the source volume is the volume of solid. From here we can see that with respect to temperature, there is two physical quantities. So G is constant. Even if you are changing the temperature, the gravity is not going to change. So G is constant, and according to temperature change, can I say buoyant force is proportional to the product of density and volume? Yes. Now let temperature increases by delta T. So now if temperature is increasing, obviously density will change, obviously volume will change, and hence the buoyant force will also change. So now the new buoyant force is Fb dash, and this is equal to density nu, volume nu, and gravity. So if we will take the ratio of these two, Fb dash upon Fb, what will you write? You will write density of liquid, density with change higher temperature, volume with higher temperature, initial density, initial volume. So what is the final density? This is initial density upon 1 plus gamma liquid into delta T. This is the final density, and yes, initial density rho L is already there, so write rho L. What is volume? Vs into 1 plus gamma S delta T divided by Vs. This is cancelled, this is cancelled. So basically, what is the buoyant force here? Buoyant force is the initial buoyant force, okay, 1 plus gamma S delta T divided by 1 plus gamma L delta T. This is the numerical formula for buoyant force when temperature is increased by delta T. Now it is interesting to see that gamma L is in denominator, and we know that when compared to solid and liquid in general, the expansion is greater in liquid. So obviously liquid expansion will be greater, so denominator is greater, and if denominator is greater, obviously the buoyant force is decreasing, it's less. So we can write on increasing the temperature, buoyant force decreases. Okay, buoyant force decreases. This is the expansion. You have to remember that solid expression will be in numerator and liquid expression will there be in denominator, and since liquid expansion is greater, then obviously denominator is greater, so buoyant force has decreased. And yes, if buoyant force has decreased, then can I write apparent weight? Apparent weight means weight in liquid is equal to true weight minus the buoyant force. What is apparent weight of a solid? That is its weight inside the liquid, the Archimedes principle, and that is different from the true weight. Why? Because some buoyancy is being acting upward. So what is the apparent? True minus buoyant. And here what we have discussed, that on increasing the temperature, what happens to buoyancy? Buoyancy decreases. So whatever you are subtracting is decreasing. It means that apparent weight will increase. So in hot water, you can say, or with high temperature, the apparent weight will increase. So hence, on increasing temperature, buoyant force is decreasing and apparent weight increases. These are the two trends, on apparent weight and on buoyancy. Moving to the next application point, that is coefficient of relative expansion. Relative expansion means we are talking about two expansions. See, this is the container, and in this container some liquid has been completely filled. As we know that volume is not for solid or liquid, rather for the space. So obviously initial volume of solid and that of liquid are same. Fine. Now let this has been supplied heat, okay, like this, and temperature will increase, expansion will take place. So let temperature changes by delta T. If temperature is changing by delta T, then final volume of solid container, that can be written as initial volume V naught 1 plus, since alpha is given and we know that alpha is the coefficient of linear expansion, so volume expansion will be 3 alpha delta T. This is for solid. What will happen for liquid? For liquid, this is V naught 1 plus gamma of liquid delta T. This is for liquid. Now see, when we are supplying the heat, when increasing the temperature, both solid and liquid, they are expanding. And when they are expanding, then it is not necessary that the expansions are same, because their coefficients are different. So the mod of expansion in solid minus expansion in liquid, the mod, which is, we can say as delta V, this is called apparent expansion. This is the expansion that will appear to us. So writing the values, V naught, this is 3 alpha minus gamma into delta T. This is delta V. This 3 alpha minus gamma, this is working as the coefficient of expansion here, because delta V in general should be V naught gamma delta T. But in place of gamma, what is written? It is written 3 alpha minus gamma. So this is called gamma relative. This is gamma relative. So what is gamma relative? Coefficient of relative or apparent expansion is 3 alpha minus gamma, that is gamma is of liquid, mod. Now according to the comparison of these two, we can see the different behavior of solid liquid expansion. For example, suppose in first case, if 3 alpha is equal to gamma. If 3 alpha is equal to gamma, obviously there is no expansion. So in that case, there is no expansion, rather there is no apparent expansion. Means the solid and liquid, they have expanded to the same extent. So we will not see any expansion there. If 3 alpha is greater than gamma, like that happens, suppose water is being boiled. So solid expansion is more, liquid expansion is less. So liquid level will go down. Liquid level falls. And when 3 alpha is less than gamma, what will happen? Obviously the liquid overflows. That happens in case of milk. Liquid overflows. So this is important question, and coefficient of relative expansion. So these were some important checklists from the expansion of solids, liquids and gases. These are the checklist points. These are the main point. NEET is going to ask you question on this. So do revise them properly and get 180 out of 180 in physics. God bless you. Stay healthy, stay happy, keep smiling.